This is a little bit of a technical. There's a technical part in the presentation. So to make it easy for you to follow with Dr. Ahmed, I do recommend that you keep a pen and a paper ready. Maybe you want to take notes, write some formulas down, follow Dr. Ahmed with the calculations. It could make it a little bit easier. So Dr. Ahmed Salama, he's the head of SFTec's technical department. He earned his bachelor's of engineering and master's degree in structural engineering from the University of Cairo in Egypt. He worked for the Egyptian Ministry of Water, and contributed to several projects during his employment there. Some of the projects he worked on is the Al-Sharika Bridges project and the Ismailia Canal. He also then came to Quebec, Canada, after being admitted to the Ph.D. program at the University of Sherbrooke to continue his studies in structural engineering under the supervision of Professor Brahim Benmokrane. He basically specialized during those years. He specialized in concrete structures that are reinforced with fiber reinforced polymers. So basically, he is an expert in this domain, and he's the right person to learn about this subject from him. He joined the SFTec in July 2019 as the head of the technical department, and he started working on several projects, redesigning and helping engineers redesigning based on FRP formulas and codes. He worked on several projects like telecommunication tower bases, water purification stations, slabs projects, ICF walls, precast walls, and everything. So he has a very wide and varied, diverse experience in FRP and different structural elements. So again, I believe he's the right person to learn from. Dr. Ahmed, the mic is yours.
Okay, thanks Outrick for this great introduction. I highly appreciate it. So again, welcome to all of you from different parts of the world and different time zones. This gives me pleasure to see a really good presence in our webinar. Please stay with us and we all will learn together. Today, I am going to talk about design of tilt-up wall panels using fiber reinforced polymer bars. In the next slides, I will go through brief introduction, field application with FRP bars, design of FRP-RC tilt-up wall panels, and finally, I will give some concluding remarks on the presented slides. In the beginning, I would like to introduce our company, SFTec. Who are we? SFTec is a professional entrepreneurial industry in the business of the composite rebar. What do we do and who do we work with? SFTec is working closely with national and international engineering firms and government departments in the construction of parking facilities, water treatment plants, and retaining wall, as well as other structures in the field. What is our focus? SFTec is focusing on the market of FRP rebar application in North America and beyond, through providing a complete design for new structures reinforced with FRP bars, and conducting research and development strategies to ensure continuous improvement of SFTec products. The question now, what is the composition of FRP materials? As per the microscopic analysis on our right side, the FRP material consists of fiber, reinforcement, resin, and the interface between them. FRP materials may be bars or sheets. We are using the FRP bars as a creative solution to eliminate the corrosion problem with a steel bar, while FRP sheets for strengthening and rehabilitation purposes. In our presentation, we will focus on the FRP bars. What are the types of FRP? In the market, we have 4 types of FRP: glass FRP, aramid, and carbon. And recently, we have a type called basalt FRP. As we see here in this stress strain curve for steel and FRP bars, there is only one difference between steel and the FRP bars, is that the FRP bars are linear up to failure without any ductility point or yielding. In our company, we are mainly focusing on the production of GFRP materials as a straight bars, bent bars, closed loops, and spirals. And also we have a product called GFRP connectors for sandwich panels. Why you must use GFRP soft bar instead of conventional steel bars? In the last 10 years, the FRP bars have been used successfully in hundreds of bridges, parking lots, tanks, and marine structures across Canada and US, as well as other parts in the world. FRP materials may offer advantages over the conventional steel bars, like longer service life, improved durability in harsh marine environment, the advantage of corrosion resistance, high tensile strength compared to the yield stress of steel, lighter than steel, no corrosion even in harsh chemical environment, neutrality to electrical and magnetic disturbance. SFTec product versus existing standards. Our materials go through strict testing requirements before they are approved for the market as a cost-effective reinforcing material instead of corrosive steel bars. The bar satisfies the minimum requirement of the specification for fiber reinforced polymer code CSA S807 to the year 2019. The bars also satisfy the minimum requirement of the Ontario Ministry of Transportation in Ontario province. The FRP bars testing are classified into three categories: physical properties test, mechanical properties test, and durability test. As an example, I will give you a detailed information on mechanical properties requirement for the Canadian standard S807 MTO versus SFT bar. This table represents the mechanical properties of grade number 3 GFRP bar of size number 6. Size number 6 here means 20 millimeters. As we see here in the first row, the tensile strength of SFT bar exceeds the minimum requirement by the Canadian standard S807 to the year 2019 and MTO by 60% on average. The elastic modulus of SFT bar exceeds the minimum requirements of the Canadian standard S807 and the MTO by 8%, as we see here in the second row. For other mechanical properties like transverse shear strength, minimum bond strength, minimum strain, our rebars also exceed the minimum requirements by the MTO classification and the Canadian standard S807. Now I will talk about precast concrete. What is precast concrete? Precast concrete is a construction product produced by casting concrete in a reusable mold or a form, which is then cured in a controlled environment, transported to the construction site and lifted into place. In contrast to the standard concrete, which is poured into site specific forms and cured on site. What are the types of precast concrete? Precast concrete members are classified into: number 1, architectural precast concrete; number 2, structural precast concrete. The architectural precast concrete refers to concrete elements that are used as non-structural cladding elements, and their most common use in precast curtain walls, as we see here on our left side. Structural precast concrete includes all elements of building, structural frame floors, roof slabs, columns, and walls, as we see on our right side. What are the advantages of precast concrete? Quick erection time, possibility of conversion, disassembling, and moving to another site. Possibility of erection in areas where traditional construction practice is not possible or difficult. Low labor intensity. Reduce wastage of material. Easier management of construction sites. Better overall construction quality. Ideal fit for simple and complex structures. What are the differences between total precast and mixed precast construction? The total precast construction is referred to a building that can be constructed totally from structural precast concrete members like columns, walls, beam, or slabs. As we see here on our left side, a total precast concrete parking garage under construction. In mixed precast construction, some structural elements of the building are made of precast concrete members like roof, slabs, or floors, while the others are made of cast in place concrete, steel, or masonry. It combines the benefit of both precast and conventional construction. The photo on our right side represents a mixed precast construction of steel frame structure combined with hollow block core slabs. Precast structural elements. We have many structural elements that can be used in precast industry. Number one, precast concrete slabs. Number two, precast concrete beams. Number three, precast concrete columns. Number four, precast concrete foundations. Number five, precast concrete stairs. And finally, precast concrete walls. In this presentation, I will focus on tilt-up wall panels. Tilt-up wall panels is essentially a precast that cast inside instead of traditional factory cast concrete members. In precast members, joint design play an important role in ensuring the concrete component act as one piece. In most cases, sealing the joint space is necessary to prevent infiltration or groundwater or liquids carried by the structures. The most common method of attachment of precast member is by use steel welded plate, as we see here on our left side. Typically, the precast members have embedded plates that can be used as welding surfaces for loose connecting or angles, as we see here on our left side. The technique number two is called rebar and grout. Rebar and grout, which is used typically within slabs. The reinforcing bars are spliced into slabs and grouted in place, as we see here on our right side. As we see here on our left side, the photo represents a beam to column connection. The detail of beam to column connection using steel welded plates. The beams and the columns have embedded plates to be welded, forming the connection between the beam and column. Slab to beam connections. As shown on our right side, the hollow core slab are set on bearing pads on precast beams. Steel reinforcing bar are inserted in the slab keyways to the span joint. The slab is then grouted. The slab may contain untopped, may remain untopped as shown on our right side, or side cast concrete topping is generally used over the slabs. The topping provides structural integration of slab units and increases the floor fire resistance and sound insulation. And finally, we have column to column connections. As we see here, column can be connected to another column by casting a concrete shoe in the upper column and putting anchors with a plate in the lower one. After that, they are assembled together. After assembling and lining the two columns, the spacing between the empty spaces will be grouted. I would like to highlight on our national and international projects with SFTec rebars. The first application we have here is the first worldwide waffle slabs, reinforced with GFRP straight and bent bars in Araya project. Another application for casting water breaks using our rebars. Another example here for casting slab on grade in Nova Scotia, Canada. Finally, we have another great field application with our GFRP connectors in precast sandwich panels at one of IBM buildings. I will shift now to another different field applications across Canada. The photo on our left side represents a project with hydrocabic for precast GFRP concrete chunk. On our right side, we can see another example for the preparation and installation of retaining RC walls for a river sea in the house. Another application for reconstructing the deteriorated slabs of one-way slabs in the rear parking garage using GFRP bars as we see here on our left side. The last field application we have today is on flat plate structure in the Chancelier parking garage in Quebec City. As shown on our right side, the flooring slabs of this two-way parking garage totally reinforced with GFRP bars. It is worth mentioning that several design codes and guidelines are available around the world for design of structural elements reinforced with FRP bars. Now I will shift to the design of tilt-up wall panels for flexure using FRP bars. Chapter 23 in the Canadian standard CSA-A23.3 for concrete structures reinforced with steel bars presents the design philosophy of this kind of walls. Here I will give the general idea, however you will see all formula in the coming slides. Number one, all of us know that tilt-up concrete walls are a well-known form of construction in North America. Tilt-up wall panels are typically slender axial load-bearing members subjected to out-of-plane lateral load from wind and seismic action. Because of their slenderness ratio, they shall be designed for second-order B delta effect to ensure structural stability that's factory performance under specified loads. The effective panel height shall be center to center the distance between lateral supports. The minimum panel thickness of a prismatic load-bearing panel without stiffening elements shall be 140 mm. The maximum height to thickness ratio shall be 50 for panels with single mat of reinforcement at the mid depths of the wall, or 65 for panels with mat reinforcement near each face. And finally, the vertical shear stress should be less than 0.09 by the concrete resistance factor by the concrete compressive strength. There are some general issues should be considered in the flexural design of any structural member reinforced with FRP bars. I will talk here on these issues according to the Canadian standard S806 to the year 2012. Number one, we have three possible modes of flexural failure of a concrete section reinforced with FRP bars. The first one is balanced failure, which represents simultaneous rupture of FRP bars and concrete crashing. Number two, tension failure, which represents the rupture of FRP bars before concrete crashing. Number three, compression failure, which represents concrete crashing while FRP bars remains in the elastic range with a strain level smaller than the ultimate strength. There is a design difference between FRP and steel, is that FRP are linear up to failure and exhibit no ductility or yielding. Another major difference is that serviceability will be more a design limitation in FRP reinforced members than with steel. Due to the lower elastic modulus of the FRP bar, deflection and crack widths will govern the design. Load factors and load combination. The Canadian standard S806 uses the same load factor as in the Canadian standard 23.3. For the load combinations are also the same in the Canadian standard 23.3, which is based on the National Building Code of Canada to the year 2015. Concrete and steel resistance factor remain in the same as the Canadian standard 23.3, while FRP bar resistance factor equals 0.75 for all FRP structures, reinforced or pre-stressed. We have a design example for a structural concrete tilt-up wall panel in a single-story warehouse building. The wall provides load resistance from three joists. As we see here, we have three joists acting on this wall. and the lateral resistance from wind load. The total height of the panel equals 9.5 meter. The entire width of the panel equals 4.5 meter as per the presented side view and elevations. The given design data here, the roof loads, the applied concentrated load and live load from each joist are 10.5 kilonewton and 11 kilonewton respectively. The applied wind load equals 1.5 kilonewton per meter square. The concrete strength equals 40 MPa. GFRP safety bar number 7 is chosen as a vertical reinforcing bar, while safety bar number 4 safety bar number 4 is chosen as a horizontal reinforcing bars. What we will do in this, we will design this wall for flexure. In the next slide, we will apply the above mentioned design philosophy of tilt-up wall panel according to the Canadian standard 23.3 to the year 2014 and the general issues for flexure according to the Canadian standard S806 on this example. In order to have a detailed flexural design for this wall, including serviceability limit stated check, these following design steps will be performed in the next slides. We are going to have heavy calculations. I'm advising you to have a paper and take some notes. The first step is to calculate the concrete dimension. The unbraced length here is simply the total height of the wall subtracted from 0.5 meters. So finally we have the unbraced length equals 9,000 millimeter or 9 meters. The wall thickness. In this example, I will use a single mat reinforcement at the mid thickness of the wall. So the wall thickness is simply equals the unbraced length in millimeter over 50. Finally, the wall thickness is 180 millimeter. The eccentricity from the roof loads equals 2/3 of the wall thickness over 2. So we will multiply 2 over 3 by wall thickness over 2. We have the wall thickness 180 millimeters, so 2 over 3 by 90 millimeters. The second step is to calculate the concrete properties in order to use them in advance. The given concrete compressive strength equals 40 MPa. According to the Canadian Code 23.3 or the CSA-806, the concrete elastic modulus equals 4,500 by the square root of the concrete compressive strength. The stress block parameters alpha 1 and beta 1 can be calculated using these equations as a function in the concrete compressive strength. So alpha 1 equals 0.79, beta 1 equals 0.89. Step number 3 is to determine the amount of vertical reinforcement and the spacing between bars. So the maximum spacing according to the Canadian standard S806 to the year 2012 equals 3 times the thickness of the wall, which will equal 540 millimeter. This one should be compared with 300 millimeters, so SL maximum equals 300 millimeter. From experience, in order to have a safe design controlled by crack widths, take S equals 0.6 from the maximum spacing between bars. So we agreed to use bar number 7 and the space with the spacing 176 millimeter at the middle thickness of the wall. So now we can calculate the total amount of flexion of vertical reinforcement that will be used using this equation. So finally, we need 27 number 7 bars bear the entire width of the wall. So we have the amount of reinforcement, we have the dimension, so we can calculate the flexural reinforcement ratio The flexural reinforcement ratio equals 0.013. The balanced flexural reinforcement ratio, according to the Canadian code S806, can be calculated using this equation. So the flexural reinforcement ratio, the balanced one, equals 0.0032. By comparing the flexural reinforcement ratio of the vertical reinforcement with the balanced flexural reinforcement ratio, the section is compression controlled, which is the desirable failure mode according to the Canadian standard S806. Step number 4. In this step, we will perform wall structural analysis. In order to do so, first we need to calculate the total gravity loads as well as the wind loads along the wall height. As I mentioned earlier, we have beaded load from 3 joists. We have B live load from 3 joists. So the total dead load we have equals 3 by 10.5. So the total dead load equals 31.5. Using the same criteria with the dead load, we have the total live load equals 33 kilo Newton. The own weight of the wall at the mid height. The own wall, the own weight of the wall at the mid height is simply equals the concrete density by the wall thickness by the area at the mid height of the wall. So finally, B wall equals 97.2. The wind load along the wall height equals the given wind load, which is 1.5 kilonewton per meter square, by the entire width of the wall. So finally, we have 6.75 per meter run. As known, in the structural analysis, we are simply using the center line of the wall as per the sketch on our right side. After calculating the ultimate loads, the ultimate factored moment is then calculated. After calculating the service loads, the next step is to calculate the ultimate loads as per the National Building Code of Canada and the Canadian Standard 23.3. According to these loads, according to these codes, the load combination consists of principal loads and companion loads. From this table, we have 5 possible load combinations that may be considered for the design of such wall under dead load, live load, and wind load. Each load combination should be investigated separately. However, combination number 2 usually governs the design. So the second load combination is considered in this example. So we agreed to use the load combination number 2 as calculated before. B dead load equals 31.5, B live load equals 33 kilonewton, B wall equals 97.2 kilonewton, W equals 6.75 kilonewton per meter run. So now we will calculate the maximum wall forces. B ultimate one, which represent the total, the factored dead load plus the factored live load. In this load combination, we have 1.25 dead load, 1.5 live load. By applying these load factors, we will get 88.8. B ultimate 2, which is the dead load from the own weight of the wall. So we agreed that the load factor for the dead load 1.25, so 1.25 by B wall. So finally we have 121.5. The ultimate wind load equals 0.4 by the wind load. So 0.4 is multiplied by 6.75, so we'll have 2.7 kilonewton per meter run. Now, and after calculating the ultimate loads, we can easily calculate the maximum factored moment. The maximum factored moment MF at the mid height of the panel, including the magnification factor due to B delta effect, equals MB by sigma B. MB is the maximum factored moment in the panel due to ultimate load at lowest stage, which deflection is computed, not including the B delta effect. To include the B delta effect, MB should be multiplied by sigma B. So sigma B is a moment magnification factor to reflect the B delta effect at ultimate loads. The bending moment diagram on our right side represent the bending moment diagram due to wind loads, due to the eccentric gravity loads. So easily we can calculate MB, which finally will equal 37.4. Now we need to calculate sigma B. Sigma B can be calculated easily from this equation. All the factors here are known for us. B ultimate 1, B ultimate 2, the unbraced length, the concrete elastic modulus. So we need to calculate the cracked moment of inertia. The cracked moment of inertia can be calculated according to the Canadian standard S806 to the year 2012. So using this equation, we will get I cracked. As we see here in this equation, all factors are known except K and NF. So K equals, the factor K can be calculated easily from this equation. This equation is mainly includes the flexural reinforcement ratio and NF. NF, or the modular ratio, is the ratio between the elastic modulus of the used FRP bar to the elastic modulus of concrete. We have calculated rho F in the past, in the previous slides. So now we can calculate rho F by NF, which will equal 0.03. So now we can calculate K. So K equals 0.22. K by D is a factor in this equation, so we can calculate it in order to make it easier for us. So K by D equals 0.22 by the flexural effective depth, which is equal 90 millimeter. So K by D equals 20 millimeter. And finally, the I crack is equal 1.29 by 10 to the power of 8. So we calculated now I crack. So the next step is to calculate sigma B. Sigma B equals 2.82. So after calculating sigma B and MB, so we can calculate easily the maximum factored moment. The maximum factored moment equals 105.5 kilonewton meter. So the step number 5 is to calculate the wall flexural capacity. The wall flexural moment capacity can be calculated using this equation according to the Canadian standard S806. All the factors in these equations are known for us from the design data, or we calculated them before, like alpha 1, beta 1, phi c, fc, the entire width of the panel, and the effective flexural depth, except the neutral depth, except the neutral axis depth C. From equilibrium, we can calculate C. C finally can be calculated by equating the compression force to the tension force in the section, and finally C equals 34.64 millimeter. So the next step before calculating the wall flexural moment capacity, we need to check the ratio between the neutral axis depth to the effective flexural depth. The neutral axis depth C over D should be greater than this formula. So we have here C over D equals 0.38, and this formula gives us 0.16. So now we can calculate the wall flexural moment capacity using this equation. The wall flexural moment capacity finally equals 212.54 kilonewton meter. By comparing the wall flexural moment capacity and the factored moment capacity, The wall moment capacity is greater than the maximum factor moment, which is good. The wall cracking moment capacity can be calculated using this equation. So finally, we have M crack equals 92.21 kilonewton meter. By comparing wall cracking moment capacity and the wall flexural moment capacity, the wall flexural moment capacity exceeds 1.5 the wall cracking moment capacity, which satisfies the requirement by the Canadian standard S806 for the flexural design. As we agreed to have a successful design for this wall, we should check the serviceability limit state according to the Canadian standard S806 to the year 2012. In order to do so, we have two checks. The first one is stress and strain limitation. The maximum stress in the used FRP bar under service load can be calculated using this equation. The Canadian standard S806 allows using 0.25 or less from the ultimate tensile strength of the used FRP bars. Here we have AF, which is the total amount of reinforcement. We have G, the flexure, the effective depth for flexure. We have D, we have MS. So we need to calculate MS first. Using the previous criteria in calculating the maximum factor moment, the maximum moment in a panel due to service load can be calculated. To do so, the service load acting on the panel should be calculated first. And finally, the maximum moment without B delta effect can be calculated. And after that, we will calculate sigma BS in order to include the B delta effect. So BS1 equals B dead load, B live load. So we have 64.5. BS2 equals the B wall, which is equal 97.2. And finally, the wind load equals 67.5. By substituting using these loads in the equation, we can get MBS. And now we can calculate sigma BS also because we have the I crack, the moment of the crack, the moment of inertia, which calculated before. So sigma BS equals 1.98. So we have finally the value of MS, which is equal 146.36. Now we are going to calculate the maximum stress in the FRP bar under service load. The maximum stress equals 168. This one is should be less than or equal 0.25 from the maximum limit of the tensile strength of the used bar. So this one is okay. Now we have the maximum strain, the maximum stress in the used FRP bars under service load. And the elastic modulus is known for us. So we can calculate the maximum strain in the used FRP bars under service load. So the maximum stress of the used FRP bars under service load equals 0.0026. When the maximum strain in the FRP bar exceeds 0.0015, the crack width parameter should be verified. So now we are going to check the factor Z. The crack width parameter can be calculated using this equation. So finally, we have Z equals 38,916, which is less than 45,000 Newton per millimeter. So we did a good job. We have we checked the serviceability limit state. We satisfy we we obeyed the maximum limits of the codes, so we are in the right way. The next step is to check the vertical shear, the vertical stress, sorry. Here by comparing the allowable vertical stress in the wall and the actual vertical stress The comparison yielded a safe design. So this one also is okay. The final step, we need to determine the horizontal reinforcement. As I mentioned earlier, we have maximum spacing of 300 millimeter, and we assumed using bar size number 4 for the horizontal reinforcement. So a single layer of a bar size number 4 is assumed every 300 millimeter at the middle thickness of the wall as a horizontal reinforcement. Based on the presented slides, the following concluding remarks can be drawn. Number one, septic rebar is a very good solution to reinforce concrete infrastructure located in harsh environments. FRP bars have been used successfully in hundreds of bridges, parking structures, pavement, builds, foundations across Canada and US and other parts in the world. In precast building, the joint design plays an important role in ensuring that the concrete components act as one piece. In most cases, sealing the joint space is very important. The flexural design of tilt-up wall panels is possible now through the Canadian standard S806 along with the design philosophy in the Canadian standard 23.3 to the year 2014. Finally, due to lower modulus of elasticity of FRP bars, deflection and the crack widths will govern the design of tilt-up wall panels. So thank you so much.